Okay, in this video we're going to be looking at the P-series test, and I think we'll do an example of two of the integral test. And both the P-series and integral test are tests for convergence, and or divergence, and we actually get the P-series test from the integral test. So the P-series test for convergence, if we have the sum n equals 1 to infinity of 1 over n to the p, this is going to converge for p greater than 1 and diverges for p between 0 and 1, including 1. So we're going to let f of x equal 1 over x to the p. Note f of x is positive for all x greater than or equal to 1. And the derivative, so f of x is equal to x to the negative p, and that's going to be f prime of x is equal to negative p x to the negative p minus 1. And if we rewrite that, that is f prime of x is negative p over x to the p plus 1. That is negative. And f of n is equal to 1 over n to the p. So all the conditions for the integral test are satisfied, so we can apply the integral test. The p integral, which we dealt with back in the improper integrals sections, 3.7, so look for the videos on 3.7. We looked at the p integral. So the p integral from 1 to infinity of 1 over x to the p dx, that's going to converge for p greater than 1 and diverge if p is between 0 and 1, including 1. So p-series, like the nth term test, those are very quick tests to determine whether p-series will tell us convergence or divergence. Nth term test will only show divergence, but those are quick tests to try. So we look at the sum n equals 1 to infinity of 1 over n. This is also called the harmonic series. Your p here is the exponent on the n, which is 1. That is less than or equal to 1 because it's equal to 1. And so this diverges by the p-series test. So very quick test. If we look at the sum n equals 1 to infinity of 1 over n squared, here this is a p-series. Your p is 2, and that's greater than 1, so this converges by the p-series test. Okay, and so that's it. Divergence for the 1 over n and convergence for the 1 over n squared. Now we're going to illustrate that the nth term test is inconclusive if the limit is 0. So if we look at the limit as n goes to infinity of 1 over n, that's equal to 0. And so the nth term test doesn't tell us anything. So the nth term test is inconclusive. Okay, and then if we look at the limit as n goes to infinity of 1 over n squared, that is also going to be 0, and so the nth term test is inconclusive here. So again, if you're using the nth term test and the limit of a sub n is 0 as n goes to infinity, you got to try something else. This series may converge or diverge, but the nth term test is not going to tell you and it's only going to tell you if it diverges. And we see two different series here. Sum n equals 1 to infinity of 1 over n and then 1 over n squared. One of them converges and the other diverges, but both their limits as n goes to infinity of their seed sequence is 0. And so again, the nth term test doesn't tell us anything here. We have to use a different test, in this case the p-series. Okay, so let's look at a couple more examples of p-series. So let's say we have 1 plus 1 over the square root of 2 plus 1 over the square root of 3 plus 1 over the square root of 4, etc. Let's write this as a series. Looks like we can start it at 1, and let's go to infinity. And it looks like 1 over the square root of n. We can rewrite that as the sum n equals 1 to infinity. Square root's the same thing as 1/2 exponent. So this is a p-series. Your p is 1/2. That is less than or equal to 1, and so the p-series test says that this is a divergent series. Okay, let's consider the sum 1 plus, well, it's not a sum yet, but we're going to write it as a sum. 1 plus 1 over 2 to the pi plus 1 over 3 to the pi plus 1 over 4 to the pi plus dot dot dot. And we can write that as the sum, n equals 1 to infinity of 1 over n to the pi. This is a p-series. P is pi, which is 3.14159, etc. That is greater than 1, and so the p-series test says that this is convergent. Okay, and we're going to go ahead and look at two examples of using the integral test. So we're going to determine the convergence or divergence using the integral test. So our series is going to be the sum, n equals 1 to infinity, of 8n squared times e to the negative n cubed. Alright, so our function f of x will be equal to 8x squared e to the negative x cubed. Notice our seed sequence, 8n squared e to the negative n cubed is equal to f of n, where n is a positive integer. So that's an agreement. Okay, f of x is continuous. Both 8x squared and e to the negative x cubed are continuous on the entire real number line, so they're certainly continuous on the interval 1 to infinity. We need to show decreasing, and so how we can show decreasing is to look at the first derivative. So the first derivative being negative would show that this is decreasing. So that'll be 16e to the negative x cubed plus 8x squared e to the negative x cubed times negative 3x squared by the chain rule. And we'll go ahead and factor out an 8x e to the negative x cubed. What's left over is a 2 minus 3x cubed, and that is certainly going to be less than 0 if x is 1 or larger, and so that's going to tell us that f of x is decreasing. Okay, the one thing that we didn't mention is it is in fact positive. 8x squared and e to the negative x cubed, those are always going to be positive, so it's always positive. The sequence agrees with the function on the positive integers. F of x is positive, is continuous and decreasing, so all the conditions of the integral test are met, so we can apply the integral test. So the integral of 8x squared e to the negative x cubed dx. I'm just going to integrate it, and then we'll put it in the improper integral form. So this is a u substitution. U is equal to negative x cubed. Du is equal to negative 3x squared dx. Okay, so we need a negative 3, so we're going to go ahead and divide by negative 3 and multiply by negative 3, so we have a nice clean substitution there. So negative 3x squared dx is deu, and negative x cubed is u. So this becomes negative 8/3 integral of e to the u du, which is negative 8/3 e to the u plus c. So it's going to be negative 8/3 e to the negative x cubed plus c. So now let's look at the improper integral from 1 to infinity of 8x squared e to the negative x cubed dx. And that's going to be equal to the limit as b goes to infinity, and we already integrated, and that integral is negative 8/3 e to the negative x cubed, and we're going to evaluate that from 1 to b. So it's going to be a limit as b goes to infinity, slide out the negative 8/3, and that's going to be 1 over e to the b cubed minus 1 over e to the 1 cubed. Okay, so that's going to be negative 8/3. Okay, as b goes to infinity, we have 1 over e to the b cubed, and so that's going to be a huge number in the denominator, and so 1 divided by a huge number is going to be 0, so, or not 0, but very close to 0. So the limit of that will be 0, and then the 1 over 1 cube, e to the 1 cube, that's a constant, so the limit of constant is a constant. And so this ends up being 8/3, 8 over 3e. It's a constant, so we can say that this improper integral converges. And so the series is going to do the same thing as what the improper integral is. Both the series and the improper integral are going to do the same thing. Since we know the improper integral converges, the series will also converge by the integral test. Okay. All right, let's work out one more example on this video, and then we'll do the last two examples on the follow-up video. Okay. This one here, we're going to look at the sum n equals 1 to infinity of n squared e to the negative 3n. Our function we're going to use is f of x equals x squared e to the negative 3x. A sub n will be equal to f of n for all positive integers, so we have an agreement there. X squared times e to the negative 3x, those are both always positive on 1 to infinity. So the function is positive. Okay. And both of them are continuous. So by both, I mean the x squared and the e to the negative 3x are continuous on the whole real number line. So the product is also. And specifically, it's going to be continuous on 1 to infinity. Now we just need to check the first derivative, make sure that it is negative on 1 to infinity. So we have decreasing, and then we have all the conditions of the integral test are met. So f prime of x is going to be 2x e to the negative 3x. Plus x squared e to the negative 3x times negative 3 by the chain rule. Factor out an x and an e to the negative 3x, and we have left 2 minus 3x. And that's certainly going to be less than 0 on 1 to infinity. And so this gives us the last condition we need for the integral test, and that is f of x is decreasing. And decreasing specifically on 1 to infinity is all we need. We're going to go ahead and look at the indefinite integral first, and then we'll look at the improper integral. So we're just going to go through and integrate this. This is not going to be a u substitution like the previous problem. It's going to be an integration by parts, and it's actually an excellent candidate for the tabular method. So u will be the x squared, dv will be e to the negative 3x dx, and so we'll go ahead and take repeated derivatives until we have 0, and then we're going to do a corresponding antiderivatives of e to the negative 3x. Its antiderivative would be negative 1/3 e to the negative 3x, and then 1/9 e to the negative 3x, and then negative 1 over 27 e to the negative 3x. Okay, and so now when we multiply, it's going to be x squared times the negative 1/3 e to the negative 3x. So we'll write that as negative x squared, and then 3e to the 3x in the denominator. Next term will be subtracting, and that subtraction comes from the integration by parts, the minus v du part. Okay, this one's going to be minus 2x over 9e to the 3x, and then plus, but it's already a minus there, so it's going to be negative 2 over 27 e to the 3x. Okay, and plus your constant integration. So now we're going to look at the improper integral from 1 to infinity of x squared e to the negative 3x dx. So that's going to be equal to the limit as b goes to infinity of x squared over 3e to the 3x minus 2x over 9e to the 3x minus 2 over 27 e to the 3x, and we're going to evaluate that from 1 to b. So that's going to be equal to the limit as b goes to infinity of negative b squared over 3e to the 3x minus 2b over 9e to the 3b minus 2 over 27e to the 3b minus the quantity negative and then 1 squared over 3e to the 3 times 1 minus 2 times 1 over 9e to the 3 times 1 minus 2 over 27 e to the 3 times 1. Okay, so what we have here is the form here is going to be minus infinity over infinity for this term here. This term, the next one would be minus infinity over infinity. And the next one's going to be 0. Those are all the terms that have b. All of this stuff over here is a constant, so that's not a problem. Okay. So the two problems, the two first terms there, we're going to have to work on them a little bit more, and we'll work on them individually. So limit as b goes to infinity of negative b squared over 3e to the 3b. And we just saw that that was the form negative infinity over infinity, so that's a candidate for L'Hopital's rule. So we go ahead and apply the L'Hopital's rule. So it's negative 2b over 9e to the 3b. That's going to give us, that's exactly this right here, and that's going to be a negative infinity over infinity. So we can apply L'Hopital's rule again. So it's going to be the limit as b goes to infinity of negative 2 over 27e to the 3b. And that's going to go to 0 as b goes to infinity. So we know that that first term is going to go to 0. Okay. Now I'm going to come up here, just because I don't have a whole lot of real estate left on this slide, and we're going to look at the second one. The limit as b goes to infinity of negative 2b over 9e to the 3b. And that's the indeterminate form, negative infinity over infinity. So we're going to apply L'Hopital's rule, and we have the limit as b goes to infinity of negative 2 over 27e to the 3b. That is also going to be 0. So the second term goes to 0. And the third term will go to 0 as well. Okay. And so what we're going to be left with is minus the constant. So the limit of the constant is just a constant. Okay, so let's erase all that there, and this improper integral is going to be 1 over 3e to the third power plus 2 over 9e to the third power plus 2 over 27e to the third power. This is a finite number, and so we can say that the improper integral converges. By the integral test, the infinite series is going to do the same thing as the improper integral. Since the improper integral is converging, so does the infinite series. So we have convergence by the integral test. Alright, so that's it for this video. Stick around for the last two examples in the next video.